Consider this satellite. It has a certain amount of total energy, the sum of potential and kinetic energy. Let's say that this satellite failed and you need to replace it. However, it occupies the position in space that the replacement needs to occupy, so you need to get it out of the way. So what we're going to do is raise the altitude of this satellite. So let's pause this and see what that would do. So we're going to take the satellite from this altitude and push it a little further out. Okay, because we're increasing the altitude, that takes a fair amount of energy to do. How much energy is it going to take? Another thing, if you don't compensate the velocity in this maneuver as well, you will change the eccentricity of the orbit, as you see here. So if you recall, the original orbit was fairly circular, and now it is much more elliptical. Okay, so what we're after is how much energy did it take to move that satellite to a higher altitude? We're talking about a change in energy. So the formula is very straightforward. The change in energy is equal to the final energy minus the initial energy. It's really important that you pay attention to the signs in these calculations. And also, let's think about this a little bit. Did the mass of the Earth change? No. Does the mass of the satellite change? No. What about the radius of the Earth? No. The only thing that's changing between the final and the initial is the altitude. So you're doing two calculations, but you're only changing one number between them. Okay, let's look at an example problem. We have a satellite with 2,500 kilograms of mass, and it's orbiting at 200,000 meters, and we need to increase its altitude to 250,000 meters to a higher altitude. So how much energy do we need, or how much energy is it going to take to go from here to here? So we write everything down that we get. We know the two altitudes and the mass. We know some facts about the Earth here. We know we're solving for the change in energy in joules, and we are using this total energy formula to help us find the energy after, the energy before, and finding the difference between them. So we're going to calculate, and right here I just do it all at once again. Break this down into smaller steps if you're not good at using your calculator. But if you look at these two calculations, the only number that changes is the altitude. So we have a negative universal gravity constant times the mass of the Earth times the mass of the satellite divided by 2 times the total radius, which includes the radius of the Earth and the altitude of the satellite. We get this number for the initial, and then after the final, we get this number because we have a higher altitude here. So this is the final number. So we put the final number here and the initial number here. And we have a negative minus a negative equals this number, or this. So 570 million joules of energy, or 5.7 e to the 8th joules. Okay, when you do these problems, I've set them up such that you don't have to type numbers much over a million. Be sure to get at least the first 4 important numbers in your entry, and you should be just fine. So again, be really careful. Watch your signs. That's where you're going to make the mistakes. So this is the most complicated math we'll do, and it's not really complicated. It's tedious. So that's all I have for now. Thanks for watching.